Good day, viewers! Welcome back to our integral calculus tutorial, wherein we, first-year engineering students, try to share our knowledge in evaluating integrals through some examples. Today, we are going to show you how to evaluate some integrals using these certain methods: distinct linear factors, repeated linear factors, quadratic factors, the Wallis Formula. And we're also going to show you how to solve for plane areas. And this tutorial is brought to you by your friendly fellows, Aya, Eugene, Jaylet, Handell, and Nicole. Happy learning, everyone! At this part, we're going to evaluate some integrals through determining their denominators distinct linear factors. This method is highly helpful once you encounter rational integrals with denominators that can be factored out into linear factors. Example number 1. The integration of the quantity x minus 1 times dx over x squared plus 5x plus 6. By looking at its denominator, we can see that it is a perfect square trinomial, and that means it can be factored out into two linear factors. So this integral is also equal to the integration of quantity x minus 1 over the quantity of x plus 2 times the quantity of x plus 3. The technique here is to disregard that you're actually integrating. We will be dealing with algebraic processes more in this method. Now, let us equate the function quantity x minus 1 over the quantity of x plus 2 times the quantity of x plus 3 to a over the quantity of x plus 2 plus b over the quantity of x plus 3. Here enters the concept of distinct linear factors, where we separate the factors of the denominator through fractional addition operation. We let a as the numerator of one of the factors and b as the numerator of the other. And if happened that there are more factors, we put c as the numerator of another factor, and so on. Therefore, through algebra, the quantity of x minus 1 is equal to a times the quantity of x plus 3 plus b times the quantity of x plus 2. Our next step is to set values for x that will nullify the value of the factors, leaving the numerators with certain values. Setting values for x applies to both sides of the equation. When x is equal to negative 2, substituting this value to the x variables of the equation gives us the quantity of negative 2 minus 1 equals a times the quantity of negative 2 plus 3. Therefore, a is equal to negative 3. We're going to do the same to determine the value of b. So when x is equal to negative 3, substituting this value to the x variables of the equation gives us the quantity of negative 3 minus 1 equals b times the quantity of negative 3 plus c. Therefore, b is equal to 4. As you can see, when we set negative 2 as the value of x, b becomes 0, determining that a is equal to negative 3. The same goes when we set negative 3 as the value of x. a becomes 0, determining that b is equal to 4. It is indeed a purely algebraic process. Thus, the integration of the quantity x minus 1 over x squared plus 5x plus 6 is equal to the integration of negative 3 over x plus 2 dx plus the integration of 4 over x plus 3 dx. In this part, we just substituted the values of a and b that we determined earlier to the numerators of the fractions with their respective distinct linear factors as their denominators. Integrating the function completely, we have negative 3 ln the quantity of x plus 2 plus 4 ln the quantity of x plus 3 plus c as the final answer. Example number 2. The integration of 3x squared plus 8x minus 12 times dx over x cubed plus 7x squared plus 12x. We are going to apply the same procedure that we did in our first example. And if you're still having trouble absorbing them all, you can always go back from the top to review it once again. So to continue, Factoring out the denominator gives us 3 distinct linear factors. So this integral is also equal to the integration of 3x squared plus 8x minus 12 times dx over x times the quantity of x plus 3 times the quantity of x plus 4. Let 3x squared plus 8x minus 12 over x times the quantity of x plus 3 times the quantity of x plus 4 be equal to a over x plus b over the quantity of x plus 3 plus c over the quantity of x plus 4. Therefore, 3x squared plus 8x minus 12 is equal to a times the quantity of x plus 3 times the quantity of x plus 4 plus b times x times the quantity of x plus 4 plus c times x times the quantity of x plus 3. When x is equal to 0, substituting this value to the x variables of the equation gives us negative 12 equals 3 times 4 times a. Therefore, a is equal to negative 1. When x is equal to negative 3, substituting this value to the x variables of the equation gives us 3 times the quantity of negative 3 raised to 2 plus 8 times the quantity of negative 3 times negative 12 equals b times the quantity of negative 3 times the quantity of negative 3 plus 4. 27 minus 24 minus 12 equals negative 3 times b. Therefore, b is equal to 3. When x is equal to negative 4, substituting this value to the x variables of the equation gives us 3 times the quantity of negative 4 raised to 2 plus 8 times the quantity of negative 4 times negative 12 equals c times the quantity of negative 4 times the quantity of negative 4 plus 3. 48 minus 32 minus 12 equals 4c. Therefore, c is equal to 1. Thus, the integration of 3x squared plus 8x minus 12 times dx over x cubed plus 7x squared plus 12x is equal to the negative integration of dx over x plus 3 times the integration of dx over the quantity of x plus 3 plus the integration of dx over the quantity of x plus 4. Integrating the function completely, we have negative ln x plus 3 times ln the quantity of x plus 3 plus ln the quantity of x plus 4 plus c as the final answer. For our last example in this method, the integration of x squared minus 5x plus 3 times dx over x cubed minus 4x squared plus 3x. Factoring out the denominator gives us 3 distinct linear factors. So this integral is also equal to the integration of x squared minus 5x plus 3 over x times the quantity of x minus 3 times the quantity of x minus 1. Let x squared minus 5x plus 3 over x times the quantity of x minus 3 times the quantity of x minus 1 be equal to a over x plus b over the quantity of x minus 3 plus c over the quantity of x minus 1. Therefore, x squared minus 5x plus 3 equals a times the quantity of x minus 3 times the quantity of x minus 1 plus b times x times the quantity of x minus 1 plus c times x times the quantity of x minus 3. When x is equal to 0, substituting this value to the x variables of the equation gives us 3 equals a times the quantity of negative 3 times the quantity of negative 1. Therefore, a is equal to 1. When x is equal to 3, substituting this value to the x variables of the equation gives us the quantity of 3 squared minus 5 times the quantity of 3 plus 3 equals b times the quantity of 3 times the quantity of 3 minus 1. 9 minus 15 plus 3 equals 6b. Therefore, b is equal to negative 1/2. When x is equal to 1, substituting this value to the x variables of the equation gives us 1 minus 5 plus 3 equals c times the quantity of 1 minus 3. Therefore, c is equal to 1/2. Thus, the integration of x squared minus 5x plus 3 times dx over x cubed minus 4x squared plus 3x is equal to the integration of dx over x minus 1/2 times the integration of dx over the quantity of x minus 3 plus 1/2 times the integration of dx over the quantity of x minus 1. Integrating the function completely, we have ln x minus 1/2 times ln the quantity of x minus 3 plus 1/2 ln the quantity of x minus 1 plus c as the final answer. This next topic is called repeated linear factors. In this topic, we will be taking factors that have exponents greater than 1 in your denominator. The process is still similar to the previous topic, distinct linear factor, but we're going to deal with repeating denominators. I said repeated since we'll be repeating a base factor more than 1, depending on its exponent. Our first example is the integration of dx over x times the squared quantity of x plus 2. As you can see, we have a squared factor, which is the quantity of x plus 2. It will be almost impossible to solve the equation if we expand it, so this is why this method was created. First step would be to arrange it through fractional addition operation. 1 is equals to a over x plus b over its base factor, which is the quantity of x plus 2, plus c over its original factor, the squared quantity of x plus 2. Do not be confused. If the factor is raised more than twice, then you start with its base factor and raise it by 1 until you reach its original factor. To continue, using the same method as a distinct linear factor, it will now be 1 is equals to a times the squared quantity of x plus 2 plus b times the quantity of x times the quantity of x plus 2 plus c times the quantity of x. If x is equals to 0, 1 is equals to a times the quantity of 2 is equals to 4a. Therefore, a is equals to 1/4. If x is equals to negative 2, 1 is equals to c times the quantity of negative 2. Therefore, c is equals to 1/2. If x is equals to 1, 1 is equals to 1/4 times the squared quantity of 3 plus b times the quantity of 3 minus 1/2. 1 and 1/2 is equals to 9/4 plus 3b. Therefore, b is equals to 3/2 minus 9/4 all over 3 is equals to negative 1/4. Thus, the integration of dx over x times the squared quantity of x plus 2 is equals to 1/4 times the integration of dx over x minus 1/4 times the integration of dx over x plus 2 minus 1/2 times the integration of dx over squared quantity of x plus 2 is equal to 1/4 ln x minus 1/4 ln quantity of x plus 2 plus 1/2 times the x plus 2 raised to negative 1 plus c. The second example would be integration of the quantity of x plus 1 times dx over x squared times the quantity of x minus 1. Let x plus 1 over x squared times the quantity of x minus 1 is equals to a over x plus b over x squared plus c over x minus 1. X plus 1 is equals to a times x plus b times the quantity of x minus 1 plus c x squared. If x is equals to 1, 1 plus 1 is equals to a times the quantity of 1 times the quantity of 1 minus 1 plus b times the quantity of 1 minus 1 plus c times the squared quantity of 1. Therefore, c is equals to 2. If x is equals to 0, 1 is equals to b times the quantity of negative 1. Therefore, b is equals to negative 1. If x is equals to negative 1, 0 is equals to a times the quantity of negative 1 times the quantity of negative 2 plus b times the quantity of negative 2 plus the squared quantity of negative 1 times c. 0 is equals to a times the quantity of 2 plus 2 plus 2. Therefore, a is equals to negative 4 over 2, or also equals to negative 2. Thus, the integration of the quantity of x plus 1 times dx over x squared times the quantity of x minus 1 is equal to negative 2 times the integration of dx over x minus 1 times the integration of x raised to negative 2 times dx plus 2 times the integration of dx over x minus 1 is equal to negative 2 ln x minus 1 times x raised to negative 1 over negative 1 plus 2 ln quantity x minus 1 plus c is equal to x raised to negative 1 minus 2 ln x plus 2 times ln the quantity of x minus 1 plus c. Next, the third example. The integration of dy over y cubed minus 2y squared. As you can see, the denominator is factorable, so it would come out as the integration of dy over y squared times the quantity of y minus 2. Let 1 over y squared times the quantity of y minus 2 is equals to a over y plus b over y squared plus c over y minus 2. Therefore, 1 is equals to ay times the quantity of y minus 2 plus b times the quantity of y minus 2 plus c times y squared. If y is equals to 0, 1 is equals to b times the quantity of negative 2. Therefore, b is equals to negative 1/2. If y is equals to 2, 1 is equals to c times the squared quantity of 2. Therefore, c is equals to 1/4. If y is equals to 1, 1 is equals to a times the quantity of negative 1 minus 1/2 times the quantity of negative 1 plus 1/4. Therefore, 1/2 plus 1/4 minus 1, a is equals to negative 1/4. Thus, the integration of dy over y cubed minus 2y squared is equals to negative 1/4 times the integration of dy over y minus 1/2 times the integration of y raised to negative 2 times dy plus 1/4 times the integration of dy over y minus 2 equals to negative 1/4 ln y minus 1/2 times y raised to negative 1 over negative 1 plus 1/4 ln quantity y minus 2 plus c, or simply as 1/2 y raised to negative 1 minus 1 over 4 ln y plus 1/4 ln quantity y minus 2 plus c. Now, for our third topic for today, we will be dealing with rational integrals having non-perfect square quadratic functions as denominators. To help you evaluate these kinds of integrals easily, we will give you a form to follow in separating the rational integrals by fractional addition. This form I'm talking about is this: a times the quantity of 2a plus b over a times x squared plus bx plus c. First example for this method is the integration of x times dx over x squared plus 6s plus 13. We can see that the denominator is not a perfect square quadratic function. We are going to split this rational function following the form that I gave you. Just like we did earlier in our first two methods, we will be dealing more with algebraic processes. Let x over x squared plus 6x plus 13 be equal to a times the quantity of 2x plus 6 over x squared plus 6x plus 13 plus b over x squared plus 6x plus 13. Since all the denominators of our equations are equal, we just only need to equate the numerators. To continue, equate x to a times the quantity of 2x plus 6 plus b. Then it will further give us this form: x equals 2ax plus the quantity of 6a plus b. In order to determine the values of our numerators, we are going to equate their coefficients. We will be equating these coefficients according to the similarities of the degrees of terms from both sides of the equation. Meaning, we only have first degree term to match to the right side of the equation. We have 2ax from the right side of our equation, which is a first degree term, so we can equate its coefficient to the first degree term from the left side of the equation, which is 1. So we have 2a equals 1. Therefore, a is equal to 1/2. Since we don't have a constant from the left side of our equation, we're automatically equating 6a plus b to 0. So we have 6a plus b equals 0. Therefore, b is equal to negative 6a. Then, substituting the value of a that we already determined, we have b equals negative 3. Therefore, the integration of x times dx over x squared plus 6x plus 13 is equal to 1/2 times the integration of the quantity of 2x plus 6 times dx over x squared plus 6x plus 13 minus 3 times the integration of dx over x squared plus 6x plus 13. To make the integration of the second function easy, we will use what we learned from our inverse trigonometric functions lesson. We are going to transform this function that will satisfy the conditions of integrating through inverse trigonometry, making the denominator into a perfect square function of x plus a perfect square constant. We now have 1/2 ln the quantity of x squared plus 6x plus 13 minus 3 times the integration of dx over the quantity of x plus 3 squared plus 2 squared. Integrating this function completely, we have 1/2 times ln the quantity of x squared plus 6x plus 13 minus 3/2 times arctan the quantity of x plus 3 over 2 plus c as the final answer. For our second example, the integration of the quantity of 4x plus 5 times dx over x squared plus 4x plus 20. We are going to follow the procedure that we did from our previous example. Let the quantity of 4x plus 5 over x squared plus 4x plus 20 be equal to a times the quantity of 2x plus 4 over x squared plus 4x plus 20 plus b over x squared plus 4x plus 20. Now, we have 4x plus 5 equals a times the quantity of 2x plus 4 plus b. Separating the terms according to their degrees, we have 4x plus 5 equals 2ax plus quantity of 4a plus b. We're going to equate their coefficients according to their degrees again. Thus, 2a equals 4. Therefore, a is equal to 2. 4a plus b equals 5. Therefore, b equals 5 minus 4a. Substituting the determined value of a, we now have b equals negative 3. Therefore, the integration of quantity of 4x plus 5 times dx over x squared plus 4x plus 20 is equal to 2 times the integration of quantity of 2x plus 4 times dx over x squared plus 4x plus 20 minus 3 times the integration of dx over x squared plus 4x plus 20. Using inverse trigonometry on the second function, we have 2 times ln the quantity of x squared plus 4x plus 20 minus 3 times the integration of dx over the quantity of x plus 2 squared plus 4 squared. Integrating this function completely, we have 2 times ln the quantity of x squared plus 4x plus 20 minus 3/4 times arctan the quantity of x plus 2 over 4 plus c as the final answer. Last example for this method, we have the integration of 4 dx over x cubed minus 4x squared plus 8x. We can see that it is a cubic function, so we need to factor it out, leaving us with one quadratic function as a factor. So this integral is also equal to the integration of 4 dx over x times the quantity of x squared minus 4x plus 8. Let 4 over x cubed minus 4x squared plus 8x be equal to a over x plus b times the quantity of 2x minus 4 over x squared minus 4x plus 8 plus c over x squared minus 4x plus 8. Now we have 4 equals a times the quantity of x squared minus 4x plus 8 plus b times x times the quantity of 2x minus 4 plus c times x. 4 equals a times the quantity of x squared minus 4x plus 8 plus b times the quantity of 2x squared minus 4x plus cx. Separating the terms according to their degrees, we have 4 equals the quantity of a plus 2b times x squared plus the quantity of negative 4a minus 4b plus c times x plus 8a. Then, we're going to equate their coefficients. We have 8a equals 4. Therefore, a is equal to 1/2. Negative 4a minus 4b plus c equals 0. a plus 2b equals 0. Therefore, b equals minus 1/2 a. Substituting the determined value of a, we have b equals minus 1/4. c equals 4 times the quantity of a plus b. Therefore, 4 times the quantity of 1/2 minus 1/4 equals 1. Thus, the integration of 4 dx over x cubed minus 4x squared plus 8x is equal to 1/2 times the integration of dx over x minus 1/4 times the integration of the quantity of 2x minus 4 dx over x squared minus 4x plus 8x plus the integration of dx over the quantity of x minus 2 squared plus 2 squared. Integrating the function completely, we have 1/2 ln x minus 1/4 ln the quantity of x squared minus 4x plus 8 plus 1/2 arctan the quantity of x minus 2 over 2 plus c as the final answer. Now that we are done with solving indefinite integrals, we will now proceed in solving definite integrals using Wallis formula. Please take note that this method can only be applied to the trigonometric function sine and cosine, and it is not applicable to other functions. Here we have the equation. The integration from 0 to pi over 2 of the overall quantity of the quantity of m minus 1 times the quantity of m minus 3 and so on, 2 or 1. Multiply to the overall quantity of the quantity of n minus 1 times the quantity of n minus 3 and so on, 2 or 1. Then, multiply to alpha over the quantity of the sum of m and n times the quantity of m plus n minus 2 and so on, 2 or 1. Wherein if m and n are both even, then alpha is equal to pi over 2. And if otherwise, alpha is equal to 1. So you focus first in your numerator, wherein you multiply the differences of m subtracted to consecutive odd integers until one of its differences is equal to 2 or 1. Same with n. Then, you multiply the product of both quantities to alpha with the following conditions. Then, your next focus is your denominator, as shown that you should multiply the sum of n and n to the differences of the sum of m and n to consecutive even integers until it has an answer equal to 2 or 1. Here comes the first example. The integration from 0 to pi over 2 of sine x squared dx. First, you find the difference of m minus consecutive odd integers is equal to the quantity of 2 minus 1, which is equal to 1, so we could stop here. Then over the sum of m and n, 2 plus 0, which is equal to, so we can stop here, is equal to 1/2 times pi over 2, which gives us the final answer of pi over 4. Next, the second example. The integration from 0 to pi over 2 of cosine y raised to 5 dy, which is equal to the quantity of 5 minus 1 times the quantity of 5 minus 3. Then, it is multiplied to 1 since your n is odd, over 5 times the quantity of 5 minus 2 times the quantity of 5 minus 4, then 4 times 2 times 1 over 5 times 3 times 1 gives you the final answer of 8 over 15. Then, the last example. The integration from 0 to pi over 2 of sine y raised to 7 dy. It is equal to the quantity of 7 minus 1 times the quantity of 7 minus 3 times the quantity of 7 minus 5, 10 times 1 over 7 times the quantity of 7 minus 2 times the quantity of 7 minus 4 times the quantity of 7 minus 6 gives you the final answer of 16 over 35. For the last part of our tutorial, we will be showing you how to solve for the area formed under a certain curve through integration. In this part, we will be able to determine definite values after we perform integration. First example for our plane area problem, we're going to find the area under one arc of the curve y equals cosine 1/4 x. We will utilize the function of our curve as our subject of integration. The technique in order to determine the area formed by the curve and its boundary is to imagine putting numerous rectangle strips to approximately measure the formed area. We don't have definite value for the area of our rectangular strip, so we're going to represent its height with the variable y and its width with the derivative of x. To be able to completely determine the area formed under the curve, we need to identify its boundaries. We can see in the illustration that we have negative 2 pi and 2 pi as the two side ends of the curve, making them as its upper and lower boundaries. To make our solution easier, notice that the curve's midpoint is exactly at the y-axis, making the left and right side of the curve symmetrical to each other. Instead of using negative 2 pi and 2 pi as our boundaries, we are going to use 0 and either of the two ends as the boundaries to make our computation simpler. So the derivation of the area under the curve is equal to y times dx. Notice that we are actually looking for the area of our rectangular strip. Next, we will integrate both sides of the equation, giving us the formula. Area equals 2 times the integration of y dx with the boundary 0 to 2 pi. Notice that we have multiplied 2 outside the integration sign. It is because we used only the half of the curve. So to make it whole later on, we need to multiply it by 2. To continue, substituting the function of our curve to the variable y, we have area equals 2 times the integration of cosine x over 4 dx with the boundary 0 to 2 pi. Performing trigonometric integration, we have area equals 8 times the integration of cosine x over 4 dx over 4 with the boundary 0 to 2 pi. Utilizing the boundaries in order to determine the definite area, we now have area equals 8 times sine x over 4 with the boundary 0 to 2 pi. In determining the area, we need to subtract the lower boundary from the upper boundary of the function, substituting the value of our boundaries to the x variable in the equation. We have area equals 8 times sine pi over 2 minus sine 0, giving us 8 times 1 minus 0. Therefore, area equals 8 square units. Next problem, we need to find the area bounded by the given curves and the lines. Y equals ln x, y equals 0, and x equals e. And we have our illustration here. We just need to follow what we did from our previous problem so that we have area equals the integration of y dx with the boundary 1 to e. Substituting the function of the curve to the y variable, we now have area equals ln x dx with the boundary 1 to e. We are going to perform integration by parts in this problem because of the constraints of our integral. We let u equals ln x, du equals dx over x, dv equals dx, and v equals x. Therefore, area is equal to x times ln x with the boundary 1 to e minus the integration of x times dx over x with the boundary 1 to e. Now we have area equals x times ln x with the boundary 1 to e minus x with the boundary 1 to e. After completely performing the integration, we substitute the value of our upper and lower boundary, giving us area equals e minus e minus. We have 1 square unit as our area. For our last problem today here in our integral calculus tutorial, we will still be having our problem number 2, but we will try another method in solving for the area, and we will find it out if we will still get the same answer as in our number 2 problem. So we have our illustration here. Notice that we still have the same graph. The only difference here is we're going to try to find the area using a horizontal rectangular strip. Back in our problems 1 and 2, we used vertical rectangular strip, so at this part, we will find out if there will be a difference or not if we also use a horizontal rectangular strip. So the derivation of the area bounded by the curves and lines is equal to E minus x times the derivative of y. We represented the length of our rectangular strip with E minus x since in the graph, we have E as our boundary for the x-axis, but the endpoint of the curve does not fall exactly at the origin, so we need to subtract an unknown distance from our origin to where the endpoint of our curve falls, giving us this E minus x variable. We represented the width of a rectangular strip with the derivative of y. Going back with our solution, we have area equals the integration of E minus x times dy with the boundary 0 to 1. Notice that we're still dealing with the area of our rectangular strip. We need to substitute the value of x from the function of our curve, which is x is equal to e to the y. Thus, we have area equals the integration of e minus e to the y dy with the boundary 0 to 1. So area is equal to e times y minus e to the y with the boundary 0 to 1. Substituting the values of our upper and lower boundary to the function, we have area equals to e minus the difference of 0 minus 1. We still have 1 square unit as our area. Same with our answer in problem number 2, using the vertical rectangular strip. So we have proven that we can either choose between the vertical or horizontal rectangular strip as our method in solving for plane areas. To wrap it up, today we showed you how to evaluate integrals having conditions that we have not seen from our previous lessons. The methods that we showed you today will be of great help when you encounter integrals with the same form. It is very important that from the moment that we lay our eyes on the integral, we already know what method of integration is to be used, which will be in favor of our convenience in solving. That will be all for today. We hope you have learned something from this tutorial, and we also hope that we have helped you widen the scope of your knowledge in integral calculus. Study well, everyone. Godspeed.